Okay, so this is the last part of the lecture. I think it's only maybe like half an hour or something. On just parallelization and transformers. So kind of like different than the stuff we covered before, but stuff on how you actually can train these transformers. Like GPT-3 is like 175 billion parameters. You can't fit that on a single GPU. That you need to train on more than one GPU. Hundreds or even thousands, and how exactly do you do that? And this is a brief summary of the predominant types of compute, just TPUs versus GPUs. I'm not going to go into too much detail over the different aspects, but there are some things to know about these types of hardware in that you can kind of interpret them similarly in terms of like flops, basically how many floating point operations they can do per second, the HBM size, which is like the memory size. So for A100s, it's like 80 gigs or 40 gigs. For TPUs, it depends, could be like 16 to 32. And another important thing, which we'll kind of allude to throughout the rest of like this presentation, is kind of the bandwidth. Mostly the bandwidth of the interconnect between different devices, which will be very important because you're training things on like 16 different GPUs, and you need to do eventually some sort of communication across these devices. And so the bandwidth of that is very important in terms of determining like how big of a model you train, how much data you want to process, stuff like that, which I'll kind of talk about. And the fundamental building blocks of all of these, at least almost all these models, are basically transformers. And then transformers, you can basically write it. It's just like 90% matmul's or like 99% matmul's. And this is exactly what these GPUs and TPUs can do. They can just do large scale matrix multiplications, just slightly different ways. GPU has many small like computational pieces, like 8 by 4 by 8, but like many more than TPUs, which do process differently using a systolic array, but in like larger chunks essentially. But in the end, the end goal of these designs is that they can process matrix multiplications like extremely quickly. Which is also kind of why I guess it's like a cycle. Like transformers work and scale really well and are fast because a lot of them are primarily matrix multiplications and they're easy to optimize, which makes people develop hardware that does matrix multiplications faster and faster. And then people do like stick more to transformers or like matmul based computation because of that. Because otherwise, if you don't do that, like for state space models, there's like less matrix multiplications. So they're sometimes just slower purely hardware wise because of that. Even though in theory, they should be faster. Yeah. Wait, sorry? This I don't know. Yeah. Okay. So we know that matrix multiplications is basically consisted of a bunch of matmuls, right? You have your QKV projection computation. You have like your MLP with the project in, project out. You have like your input dense layer, your output logic layers. It's all matrix multiplication. So the fundamental building block of sharding a model across multiple devices, let's say if we have like 1,000 GPUs and we're training one model, how do we shard our model, or how do we divide our training so that it can actually run on all these GPUs and also efficiently? And the building block of this is just matmul sharding. So if you want to multiply two matrices, so y is equal to xa, all of them are matrices. They can be whatever shape, let's say all squares for now. You can do different kinds of sharding. So let's say if you do row sharding on A and column sharding on B, so defined by the different colors. Then this is just how matrix multiplication works, is if you multiply it out, that times that is a part of the top left. Let's see. So yeah. So actually, we can just start from here then. So what happens if you multiply this chunk, so this first the first row of this two columns by the first column of the two rows, then you'll get basically a partial sum of the top left component, because the full sum is easier if I just go, is like the full sum is this times this, but now we're doing only, let's say, half of it. So this times this. And so what that means is that let's say if that partial sum is y1, then y2 would be like this thing times this. So this is like one way of sharding the matrix multiplication, because in this case, you're sharding like the addition part of that dot product. And then what you can do is if you multiply, let's say, that first half row with all of the half columns, then you can get the partial sum of that entire row. You can do this for the whole matrix. So basically, if you multiply these two halves, then you'll get basically a partial sum of like the entire matrix. So the full result is the sum of these two. So you're basically breaking up this computation. You're breaking up this one matrix multiplication computation into two separate matrix multiplications, where it's the green parts is on one device, let's say, and then the blue parts are stored on device 2. And the question is, how can I compute this entire matrix multiplication result? And you can do the partials on each of the devices separately. And then after that, you have to do like a reduction across the different devices to sum them to actually result in like the original Y result, or the full output result you want. Any questions about this? Okay. And this is a different way of sharding. So let's say if you have your full X stored on one device, and then you have, let's say, the columns or half the columns of A stored on, like let's say the first two columns A stored on the first device, then if you do a matrix multiplication, then what you have is not the partial sum, is you just have a section of the output now, right? And then let's say in device 2, is there another slide? Oh yeah, okay. In device 2, you would have like a replicated copy of X. So X is the entire tensor X would be stored on device 1, and the entire tensor X would be stored on device 2. And then device 1 would carry A1, device 2 would carry A2, and they each compute the matrix multiplication of its own like part of A. And then so each device would have its own like half. And then in the end, if you want to communicate the full result, you can just do like a gather, or you can communicate each half to each device to have the full result. So just kind of keep in mind that this is where like the communication part comes in terms of like the bandwidth of like the faster the communication, the less overhead. Because in this sense, the communication does have a cost because you have to wait for the results to come in. If it's super fast, you don't have to wait that long. If it's really slow, it may be like a major bottleneck in your network. So this is like a lot of information. But this is how the matmul sharding works in like different kinds of linear layers. So let me see if there's do I have another slide here? Okay, let's just talk about this then. Okay, so you have X here, so this is your input. And then we can ignore this for now. So what happens is that you can shard X into two parts, and then you can do your kind of like the partial sums as we kind of described. And then this is basically what was in the first set of slides we do, where the X and the A's are both sharded across. And then if you want to compute the entire Y, you can do an all gather. So G here is an all gather, or in this case, what we call an all reduce. Basically, an all reduce is it will take every device in your network, and then it would sum up that same tensor across all the devices. So in this case, you have two devices. So the all reduce will compute y1 plus y2 for every device, and in the end, y would be stored on every device. If you had three devices, it would be y is equal to y1 plus y2 y3, or y1 plus y2 plus y3. And then the part I did here is f here. It's like, so I guess f here is a split. So x is split into x1 and x2, similar to how we show in the diagram. And then the way you do your backward pass, which is kind of what this here is for, is that in here G is just identity backward pass, and then here F is like an all gather in your backward pass. Because one way to think about it is when you're back propagating, now you have the partial gradient of like dl dx1 and dl dx2. But now you need dl dx, and And it's like basically the reverse of what our forward process was. So instead of splitting, we gather and sync across devices. And then column parallel is similar to the second one that we described, where in this case, so F is identity in this case, and X is replicated. And then now A is split over columns. And then you can compute Y1, Y2, and then you can do an all gather to get your full Y. And the backward pass is in a similar fashion. So since forward pass was all gather, now backward pass here is where we're splitting the gradients. And then we back propagate. And then in that last part, we essentially have gradients from each of the sections of A. So you have to do it in all reduce over your devices instead. Yes. The answer is like a combination of these two, I think, which I'll talk about. Which, we'll see. Yeah, it'll be the slide after. I guess this I already just talked about. So we can just skip this. Okay. So this is how it's done in practice, which is a little bit more efficient. Basically, the idea is you want to reduce your communication as much as possible. Like communication is an overhead you want to like reduce. And so the less communication operations you do, the better it usually is. So this is an example of like the MLP. So basically you have your input X and then you project out into like a higher hidden dimension and then you project back down. And the way this works is that you can basically do replicate and then column sharding here. So in this case, X is not sharded, and then only your weight matrices here are sharded, A1 and A2. And then so you compute that matmul, you compute your activation as usual in the MLP, and then so you have Y1, Y2. And then usually here in the standard thing, if you wanted Y, you'd have to do an all gather. But because of the way this is constructed is that you can take advantage of that this thing is already sharded. And then it's like the row sharded version now. Because in the row sharded version, we had to take let's say X and we had to split it into X1, X2. But here it's already split into Y1, Y2. So then we can just feed it into like a row parallel version and then have the sharded B1, B2, do the computation, and then G there would be an all reduce. And then the backwards pass would be kind of similar to what I described, where G would be identity, and then F there would be like an all reduce in the backwards pass. But this is like the fundamental building block of how like the MLP works. And also very similar, which I'll show is how the attention works as well. Yes. What is, sorry? B is the weight matrix that will map from, so let's say for the standard MLP, A would be like it would map from dimension D to 4D, and then B would be a matrix that maps from 4D to D. Yeah. Any questions about this? Because this is probably, if you're gonna take away one thing, it should be this. Yeah. Yeah. In this case, they're already pre-split. They're permanently stored on separate devices, and they will never be communicated collectively because you just don't need to. So it's like when you initialize, it's already split. Yeah. Yeah, exactly. So if you have like another copy of it, it will just be the same, like an exact copy of this. So it reduces this unnecessary communication in the middle, basically. Cool. Anything else? Yep. I would say, yeah, like yeah, this is like GPU 1, this is GPU 2. Yeah. Yeah. It depends. If you're doing a PyTorch, it's explicitly coded. Yeah. if you're doing in JAX, they can sometimes do it for you. Yeah. Cool. So attention is kind of the same way. It's basically identical structure. So you have X here. It's replicated, and then in this case, your QKV projection matrices are sharded. And the nice thing about this is the way it's sharded is that it's sharded by heads. So let's say if my attention layer has 4 heads and I have 2 devices, then each device will in the end see 2 heads, or like store 2 separate heads. And then the attention computation between heads is like fully independent, right? You can do that separately. So there's no like cross head interaction, at least in the beginning. So you can do your standard thing of doing computing your Q and K, dot product, softmax. You can do dropout, and then times your value, and then you get Y1, and also Y2. So these are the results from the 2 different sections of the heads. And then now it's like the similar thing where it's already split in Y1, Y2. So then the output, because it also, attention has also the, like an output projection that essentially mixes across heads. So then you can do a similar thing where you shard your output dense layer into 2 parts, do your multiplications, and then G there is another all reduce. It's like almost identical to the MLP style. Yeah. Yeah. Sorry? Sharding and parallel? Oh, sharding is parallelizing. Like they're one and the same. Or they are the same. Yeah. Yeah. It's parallelization. I need to compute one big matmul. I can do it into 2 halves on 2 different machines, on 2 different devices. So, optimally it'd be like 2 times faster. So yeah, there's time speed up, and then there's also, well, I guess the main purpose would be, well, there's time speed up, but the other benefit would be you're sharding your parameters. So if you have a really, really big model, then you're dividing your parameters across different devices, so it saves memory there. Yeah. Why we're not sharding QKV, or? Well, in this case, they're already sharded because the projection matrices for QKV are sharded. Or I'm not sure if I fully understand your question. Well, they will receive different updates. I guess there's no purpose to sharing them. Okay. So that was like a general way of you can do sharding and transformers. And now I'll be talking about explicitly how this sharding is kind of used in terms of different forms of parallelism. Just covering a few of them. There's a lot of different kinds, but I'll cover like a few main subsets. The first one, a lot of you could be familiar with, is just data parallelism. If you just train anything with PyTorch DDP or PyTorch data parallel or any of that, it's just data parallelism. Where here you can basically treat, let's say the way to understand this diagram is just some tensor, and it's just the y here is the batch dimension, where each row is a separate batch element, and then the x or the horizontal is your hidden dimension, or like your representation, some e dimensional representation. So it's like the shape of this is like batched by e. Okay, and then the weights is, let's say, an e by e matrix, and the output is like also batched by e because we're multiplying an e by e matrix. And data parallelism is simple. So this you can treat each color, let's say green as device 1, blue as device 2, and then in this case E would be like it's like replicated across both of them. So that's why it's yellow. So I guess green and blue make yellow, maybe. Forgot. But yeah, that's replicated. So this is like something that most of you have probably done if you've trained anything on multiple GPUs. Where in this case, it's like split across devices. So you can see E there is replicated, and then your batch is split. So let's say you have a global batch size of 4, you have 2 devices, you can do a batch size of 2 per device. So this can save you memory. It can also save you time, depending on what your main constraint is. Okay, so that was data parallelism. There's another very popular parallelism method called fully sharded data parallel that is fairly easy. It's very, very useful and also pretty easy relatively to understand. So it's still fully data parallel in the sense that each device will see its own batch. So each device will see like two different elements, let's say. And then before in data parallel, you would replicate your weights across all the devices. But now in this case, let's say what happens if we sharded them across all the devices. So device 1 has half of this matrix and device 2 has the other half. And then we want to compute the output. I haven't gone exactly into how the output is. Well, I guess, yeah, actually the way it's sharded here is that the way you compute the output is like, so for device 1, you do your forward pass on the green blocks. And then now to do your multiplication, you kind of need the full matrix. So you do an all gather. So you all gather across all your devices. So basically after the all gather, every device will see the entire E matrix, almost as if it was replicated. You can think of it that way, which I'll kind of explain how this is actually useful later on. But once you have the full matrix, you can then do your standard forward pass matrix multiplication and compute the batch. But the nice thing, which kind of stressed here, is that you only need to do this one layer at a time. Because in standard data parallelism, you replicate your entire model across all the devices. So every device at all times stores the entire parameter weights of your model, which could be really big. 175 billion is like 700 gigs, or it could be like 350 gigs, depending on precision. But the nice thing about FSDP, I guess that's what it's called it, as an acronym, is that you only need to do it one layer at a time. So let's say while I'm computing, so let's say at layer I-1 here, I've already all gathered my E, so I have the full E by E matrix, and then I'm doing that computation. While I'm doing the computation, I can asynchronously communicate the layer after, right? So this is over. So there's no conflict here. The device can do communication and it can do computation at the same time. That's like kind of the key thing. So basically, as long as your computation takes long enough, such that by the time it finishes computation, it reaches the next layer. Hopefully, it's already been all gathered. You can do the computation, and then you can move on. And then once you've done the computation, you can then split the E back up, and then like keep the shard of the specific device. So that's like why it saves memory. It keeps the entire weight matrix, but only for like a single layer at a time, which is much cheaper, especially for like really, really deep networks. Okay, so one moderately like mathematical aspect of this is like the Coinbase I kind of mentioned. It's like, as long as my computation time is long enough such that it's longer than the time it takes to all gather for the next layer, there won't be any extra overhead. So then the question is like, what is the criteria? Like, what criteria does my model size or my training batch size need such that this is sufficient, such that I'm doing enough computation on a single GPU such that when it's done, the next layer is already all gathered and ready. And the way this is done is kind of through some like computation of like arithmetic intensity and kind of like the bandwidth of like your network. So the way it works is the first bullet point is we have our matrix multiplication. So this is a batch by E times a E by E matrix. So the flops is 2 times batch by E squared. And all gathering require, and then it's like, so I have that many flops for the matrix multiplication. And then if you want to all gather, how many bytes do I need to communicate? And that's like roughly 2 times e squared bytes if you assume half precision. Because you just need to communicate the entire weight matrix everywhere. And then arithmetic intensity. So this is a metric that's pretty commonly used. So this is essentially the ratio of the number of flops I'm doing, the number of flops for my computation and the amount of communication I need to do. So it's just the first bullet point divided by the second bullet point. So this turns out to be equal to just batch per chip flops divided by byte. It's like B essentially. And the second part, or the last part, so we know the arithmetic intensity of like how many flops it does per byte of computation, or how many flops it does per byte. And the last part to figure out, how large my batch size actually needs to be depends on just the bandwidth of like your device. So ICI is, I believe, inter-chip interconnect. So it's the connection between multiple TPUs, or on GPUs, it would be the bandwidth between multiple GPUs. And in this case, the time it takes to transfer data between devices is, the intensity is roughly 1018 flops per byte. So in order to make it so that our computation is at least our communication, is that we would need at least batch per chip flops per byte. So that would basically mean we would want the batch per chip to be like larger than 1018. And at that point, in theory, there should be no overlap, or there should be an overlap, yeah. As long as your batch size is sufficiently large per device. So in this case, if you wanted to train on more devices, you would be training on a larger batch size. Yeah. Which after a certain point is like, yeah. 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 In this case, no. They're kind of interchangeable. Yeah.
So how are the different machines like synchronized, or?
You mean like how like an all reduce is done, or how these collectives are done?
I guess that how it kind of has to do with like synchronizing the computations on the two machines, and it seems that something that's parallel would be using the same clock.
In this case, it's like kind of using the same clock in the sense that the way these codes will work is that, let's say each device runs the exact same sequence of code, like exact same sequence of function calls. So they will all call all reduce at the exact same time, or like they will all call all reduce at the same as like the nth command they run. So some devices could be behind, but the ones that are ahead will just be blocked until all the other ones call it.
Or a layer or a group, right? Different types of normalizations. Are these more expensive in this case because you kind of like need the whole world kind of to compute, or is there a way to like pre-compute some of these things to make it more efficient?
Pre-compute is hard. It depends on normalization. So most of these transformers use layer norm. So in most cases, you won't shard over the activation dimension. You only shard over batch, and for that, layer norm doesn't need any extra communication. If you want to do batch norm, you do have to communicate. Like PyTorch has like a sync batch norm that will communicate the mean and standard deviation and it does add some extra overhead. Yeah. Okay, this is So we talked about FSDP, and this is tensor parallelism. So this is another way to shard. This is exactly what I described way before in like the way the sharding for the MLP and attention works. To some extent, yeah. But in this case, I guess one other way you can do it. So I guess there's two ways of tensor parallelism. There's you can shard it like here, in which you don't shard the actual batch, but you only shard the weights of like the QKV and then like the output projection. That's one way of doing tensor parallelism, which is like fairly standard. One other way you could do it is that in addition to sharding the weights, you can shard over your activations here, which I think is in practical applications is a little bit less explicitly coded, but it still could be used. And this is very similar to the sharding matmul stuff that I talked about in the beginning. So now you have, in this case, you can do like your partial multiplications, and then now you have like partial sums, and then you can in this case you can do a reduce scatter, which you can imagine as just like an all reduce to compute the entire output, and then you can then reshard, which is kind of like the scatter operation. So each device still only has its own portion. And then you can combine these. You just get more colors. So you can do FSDP because they're not conflicting in any way. You would just need to change how you do your devices. So the easiest way to think about this is, let's say you have 16 devices, and then you want to figure out which devices you want to do tensor parallelism, which devices you want to do FSDP. Then what this turns out to be is like a 2D grid. So if I have like a FSDP of like 4 and a TP of 4, that would be like 16 devices. So basically if I had like a batch size of like 4, then each FSDP or each data parallel rank would get a batch size of 1. And then that would be fed through like a sequence of like 4 devices with tensor parallelism across it. And in the end, you can do like some pretty complicated computations. It just gets more, I guess, more annoying to code. Yeah.
Question. I'll really like lay it all out here. At the same time, I'm thinking about when I implement something like this, I would hope that it's just kind of built in. And I can just say, this is my model size. This is the GPUs or TPUs I have available. You just pick whatever is best and do it that way. Chart it the way that's fastest or most cost effective.
Yes.
No.
No.
Why not? Possible, right? Because the way you explain it, I mean, there is a math to it.
So
There's logic to it.
in terms of choosing the sharding, that is definitely not, that is manually done right now, but it could be done in the future. I think it's not too hard to optimize. But even coding this parallelism, like PyTorch is like pretty complicated. Like FSDP is very complicated, especially if you want things to overlap when it communicates and does computation. JAX is a lot easier, I guess, since it does that all implicitly if you use JAX. Where you don't actually, because what JAX does is it will treat the, let's say you have 1,000 devices, it'll treat all 1,000 devices as one single device. And then JAX's job would then be to like, you can define a certain sharding constraints of how matrices are sharded, but it will figure out when it compiles the graph, it will figure out what collectives do I need to do this computation. Versus for PyTorch, at least for now, you have to explicitly code every communication. Yeah, which is not ideal, but it's also less prone to like JAX can do stupid things where like it will do collectives where you don't want it to. And it can slow things down a lot, and it's hard to debug. But when it does work, it's very nice. Whereas PyTorch doing everything explicitly is annoying, but it could be less error prone. But yeah, to answer your question, it's like it's still like a non-trivial amount of work. Yeah. So the easiest way to think about, let's say between FSDP and TP, the main difference between these two is that they're both ways to shard your model in some sense. The main difference is that FSDP still requires a batch size of 1 per device. So if I have 1,000 devices, I need at least 1,000 batch size. Versus for TP, I can have a batch size of 1 across, let's say, 4 devices or 8 devices. So that also lets you, like, if you increase the TP allocation for your devices, you can train on like a lower batch size, which may be something you want if a single batch doesn't fit in a single device. If you're training on like a 100,000 length sequences, then that probably can't fit in a single batch. So then you can parallelize it with TP to fit that in memory. But in general, it's like as much FSDP as possible. That's like the general rule of thumb I follow. Yeah, you would probably need to use. Well, that I'm not sure actually. It's not. Yeah, right off the top of my head, I don't know the answer to that. Okay. I think I already talked about this. Okay. Yeah. Cool. Yeah, that's pretty much it. Any other questions about anything? Yep. Best thing is to maximize FSDP. Oh yeah, but that's not too hard. I think that's not too hard. Yeah. So at least with the current way some TPs are implemented, is it's like blocking. Or there are some things about memory, but anyways, so like one aspect of it is blocking. So G there is an all reduce. You can't really overlap that with anything because it has to compute the entire output and then it can feed it forward. Versus let's say FSDP, it can be fully overlapped, which will in the end result in no overhead. So and then there's some aspects of TP which is a little bit less memory efficient because like here it does like a replication, which is not ideal. So it's like a little bit less memory efficient, and it could be a little bit, it could be sometimes a little bit slower. Usually I just found that like if your batch size is large enough, then do FSDP and it just is better. Yeah. I would, well, if it's a Hugging Face model, then you just hope and pray someone's done it for you somewhere. Yeah, that's hard. I also don't work that much with them. If it's just implementing a transformer sharding, then I just recommend JAX or something. It's like significantly easier. In JAX. or if it's like a popular enough model, let's say Llama or something, then yeah, there are implementations with shard it. There's no official implementations. But like there's like I use like what is it called? I forgot what it's called. It was some inference library. The one from Rise or now. No. I don't know why I forgot. But anyways, those support like let's say like tensor parallelism. I think is the main one that it supports. Aside from that, there isn't really anything else. Aside from implementing yourself, which is kind of annoying. Those are mutually exclusive. You can do both of them. Because attention sharding I explained was over the heads, and the ring attention is over sequence length. So you can technically do both of them. Cool. Okay, I think that's all the questions. Is that a question? Okay. Cool. Yeah.